So the most commonly requested problem, 4 people requested this one, is choice exercise 8, this 4-question problem. Sometimes this is called the coupon collecting problem. So that's worth knowing that name. You might see it in other contexts. Okay, so we're trying to collect these Pokemon cards, and there's 8 different cards we want to collect. And sort of each trial that we're gonna get one of those 8 cards uniformly at random. Okay. And what we're trying to do is how many packs do we need to collect to get all of them? Like how many times do we need to try? And it's going to depend. Like we could get really lucky and we could get all of them in 8 tries each time we get something new, but more likely you would expect it will take more. And the question here is how many more? What do we expect? So in this problem here, we're gonna start off with A, and A is kind of abstracted away from the context of the problem, but A is going to help us answer other questions here. So A, we have a series of independent events occurring, each succeeding with probability P, and then X is the number of tries before success, before and including success. So if we have the failure, success, then X equals 4. If we have a success on our first try, of course, X just equals 1. And this asks what's the PMF of X. And so the PMF of X is going to depend on K, and it's going to be what has to happen for our first success to be on the 4th try is that we first need 3 failures. And for it to be on the kth try, we first need K minus 1 failures. And the probability of success is P, so the probability of failure is 1 minus P. So we have 1 minus P to the K minus 1, and then we need to have that success on our kth try, so that's going to be times P. So this is our PMF, and this answers our first question here. Okay, the next part also, we can forget about the Pokemon card problem for a minute. We're just asking what's the expected value of X, and it's going to depend on P, the probability of success. And here's the idea, is that if 2 things. So the first thing is that X, we're going to say, is distributed like geometric P. In fact, this is like how we construct a geometric P. Number of trials before and including success. And we know, because X is geometric P, that things that are distributed like geometric P are going to have expected value of 1 over P. Okay, we can kind of use our intuition here. If we're rolling a die and we're looking for some particular number, we want to roll a 4 or something, then because we have a 1 in 6 chance each time of rolling a 4, we sort of, at least naively, expect maybe that you need to roll on average 6 times in order to get that success. Okay. But there's another way we could do it. Also, if you love calculus, we can compute this expected value. So the expected value of X is going to be the sum as sort of K goes from 1 up to infinity of K times that PMF of X, which I'm going to write the PMF of X like this, 1 minus P to the K minus 1 times P. And we're going to note, hey, that's our PMF of X evaluated at K. Okay, and this, it turns out, we could also see equals 1 over P, although it's definitely like not super obvious. Okay, so that gets us to C. So C, I think, is where a lot of people had confusion. Maybe I could have written this more clearly, but let's do it. Let's do a Pokemon example. So example. Let's say that on our first try, we get a Leafeon in our first deck. And then on our next try, we get a Glaceon, and then a Sylveon, and then we got a Sylveon again on our next try. and then we got Vaporeon. And then, okay, we got a Glaceon again, and again, oh man, we keep getting Glaceons, and then we get a Flareon and an Espeon and so on. Okay. Okay. The reason that I'm doing this is let's highlight all of our unique cards. So, okay, that was a success, that was a success, that was a success. Our fourth try wasn't a success because we got a card we already had. That was a success. Our next two tries weren't successes. Okay. And now I want to use this to illustrate what's going on. It took us one try to get our first unique card. So this is our random variable in part C, y1. And we have y1 equals 1 because we got one on the first try. Okay. And then again, in this story, based on this outcome, our y2 is also 1. It took us one try to get our next one. And similarly, y3, also 1. But y4 took 2 tries. So y4 equals 2. And y5, well, that took 3 tries. So y5 equals 3. But then for y6, which is we got after that, once we got our fifth card, our sixth card we get in just one try. Okay. So here we have y6 equals, y6 is going to equal 1 here. Okay. And if we add these all up, y1 plus y2 plus y3 plus y4 plus y5 plus y6, we're going to get like the number of trials that it took to get to the point where we have 6 distinct cards in our hand. Okay. So, what's this question asking? We have y1 equals 1, like we always get a new card on our very first try, and then yi is the random variable that tells us how many packs we need to open after we get a card before we get the next card. And so yi is going to be greater than or equal to 1. And this asks what's the expected value of yi. Okay, and we're going to use the ideas from A and B here. Okay, so let's do C here. And we know that the expected value of y1, well, that's just going to be 1 because it's always 1. So it's 100% of the time. How about our story for y2? y2, here, when we're doing this, until we get our second card, each try, we have a 7 out of 8 chance of getting a new card. Because we have one of the cards and all of this other 7 are equally good for us getting a new card. Okay, and using our idea from B, we're going to have that the expected value of y2 is we take the reciprocal. We do the 1 over p. Okay, and this is good because we should expect something that's more than 1. On average, it takes slightly more than 1 try. Okay, and similarly, y3, we're going to see the pattern really soon here. Here, it's kind of the same story, except for now this story is in pink. All right. And in this story, each try we have 2 cards, so there's 6 more we're trying to get. So each try we have a 6/8 chance of getting a new card. And so this is going to be 8 over 6. And so on. And what we see is that the expected value of our ith card is going to be 8 divided by 8 minus I plus 1. Right? So here, sort of the denominator, we could think of this as being 8 over 8 and 8 over 7 and 8 over 6. And all of these numbers, 6 is 9 minus 3, 7 is 9 minus 2. If we thought of this as 8 over 8, we get that 8 is 9 minus 1. So it's 8 over 8 minus I plus 1. Okay, and now we're asked, for D, what is the expected value of y1 plus y2 all of the way up to y8? And we're gonna say what this represents. Well, what does this represent? It's gonna represent the number of tries until we have all 8 cards, right? Remember, when we added all of these up, we got the number of tries until we had 6 unique cards in our hand, or 6 distinct cards in our hand. And if we add up to y8, it's going to be until we have all of them. So D is the number of tries before acquiring all 8 blankions. All right, and so that's the expected value of y1 plus y2 all of the way up to y8, which of course is the expected value of y1 plus the expected value of y2 all of the way up to y8. Right, that's just linearity of expectation. And moreover, we know what all of these things are. I'm going to write this as our 8 over 8 plus 8 over 7 all of the way up to 8 over 1. Okay, and then I'm going to factor out, actually. I'm going to call this 8 times 1/8 plus 1/7 plus all of the way to 1 over 1. And we can compute what this is. We have a bunch of different tools to compute how we can do something like this. In R, I would probably do something like 8 times 1 divided by 8 colon 1, and then I would sum this up. So this is in R. Okay, and if I do that, I'm doing that right this minute. If I do that, well, I get that this here, it's definitely going to be bigger than 8. And then this thing here is plus 4, so it's definitely going to be bigger than 12, and so on. And when I add all of these up in R, I get that this equals approximately 21.74 packs. Okay, so that's our expected value. Okay, in part E, we're just going to do this, but now we have 1,000 cards to collect. And then in part F, we get to name our final card. Part F's the most important part of this. And so how's part E go? E with 1,000 cards. Now we're just going to do 1,000 times 1 over 1,000 plus 1 over 999 plus up to 1 over 1. And we can do something essentially similar to this in R to compute it, which I'm doing right now. Okay, and what I get for this is now it requires, on average, we're going to open 7,485.47 packs to try and get our 1,000 evolutions of EV, including, and I'm having to do problem F, which is our 1,000th evolution. I think that our 1,000th evolution is in the year 2093. So I think We're going to call this one Holkion. Yeah, after that whole pause, this is the best thing that I came up with, is number 1000. Okay? All right, see you in the next video.